Good afternoon, everyone. I'm Chen Tian from Nanjing University. Today, I'm glad to present our paper. It's a congestion control paper again, and we are glad that we have been awarded the outstanding paper this morning. This, as you said on title, is a 01-step convergence and readily deployable congestion control protocol for the data centers. It's used to be my students. Actually, 80% of the work is done by my students, my student Zhao Chen Zhang, and other authors. We both mainly contributed to the discussion, but unfortunately he's not here due to the visa problem. So, as a professor, I haven't been here for 14 years. It's usually presented by the students, so I will try my best. Okay. So now we come to the motivation part. Congestion control is a typical algorithm. Everybody knows it from the textbooks. Now in data centers, our congestion control, we need a convergent speed. There are two reasons. The first one is that currently our workloads in data centers mostly follow the on-off pattern. It's just on in several microseconds and off in several seconds. It's very quick. So our congestion control need to catch up with the frequency. This is the first problem. The second requirements are bandwidth always doubles, keep climbing. Okay, we from 100 Gbps to 800 Gbps, and later maybe 1.6 T. Okay, there are larger state gap. Okay, we need to converge even faster to catch up with the increase of the bandwidth. Okay, two trends. Okay, this is our first contribution. We actually defined the notation, a big O notation. We borrowed a big notation to characterize, to describe the a formal description of the convergence speed. I think it's natural to all our computer science guys. In common algorithms, we input size n, and then we have some time cost to run the algorithm. Then we can describe the algorithm as O1 O log n, On O log n, O1. Okay, so we borrow the same idea. Here, the input size we mimic with the state of gap. The gap means the current rate and the target rate. That's delta. Okay, we make it to the input size, and the time cost we found an increment means the number of updated steps. Okay, how many steps do we need to converge to our target rate? Now finally we can get a similar notation of O delta, O log delta, or O1. Okay, so among all these classes, the best one is O1 step convergence. That means our congestion control can reach the target in a constant number of steps, okay, regardless of how big the delta is. That's our idea solution, okay. But different, as we can see, different congestion control algorithms, they have different convergence speeds. Here is a simple, very typical example. We have one long flow and 9 short flows, and we have a microburst from 1 millisecond to 5 milliseconds. As we can see, if this is an ideal congestion control, okay, it will get this is normalized, so it will be 0.0 from 0 to 1 milliseconds, and be 0.1 from 1 millisecond to 5 milliseconds, and quickly restore to 1.0 link capacity after 5 milliseconds. And this is what we can see. Typically used DCQCN. This is typically deployed in current data centers, and we can see the decreasing speed is O log delta, and the increasing acceleration speed is O delta. It's very slow, and this is the Poseidon in recent years publication. Both the deceleration and acceleration is O log delta. Okay, I will not explain the details here. And this HPCC is actually very good. It really achieves O1 convergency. Okay, this is a rather ideal format. And we give a comparison here. This is we list all the congestion control papers here, and we can see that their convergence speed. You can see here we have 3 kinds of congestion control. They can actually already achieve O1 step convergency. But this is the problem. Okay, none of them are deployable. Let's say readily deployable. Okay, for example, this precise-INT-based HPCC and PowerTCP. Okay, they need some special hardwares and receiver-driven, and they all have their problem. Receiver-driven might need a non-overlap topology. And this switching-driven is very traditional. They need computational capacity support. So none of them are readily deployable. So now in this paper, we presented the first readily deployable congestion control that can achieve O1 step convergency. Okay, this is the first we want to show. O1 step convergency. Actually, it boils down to one-step convergency. As we can see from this figure, in the left part, you can see if each step there is a delta gap between the between the target and the current state. If every time we close a fraction of the gap, that means still a log delta complexity. And here, but eventually at one step, we need to close the remaining delta entirely. That means our algorithm need such a algorithm that we can close it in one step. So the question comes to how do we make a single step close delta entirely? Okay, this is our first principle. Okay, to achieve one step close, we need MIMD. That means multiplicative increase and multiplicative decrease. This is a lot of math. We will make it simple. This AI is not artificial intelligence. It's just our familiar additive increase. Okay, so if we use additive increase, as we can see, for a specific flow, it's plus. Okay, so the aggregate rate of n flows is the aggregate of n plus n multiplied alpha. So if we want to close the gap in one step, we need to do alpha. This increase equals to delta over n. But no one knows what n is. It's congestion. N is the congestion number of flows in the bottleneck. No one knows it. So basically, it's not achievable. But if we use multiplicative increase, as we can see, it's a factor of multiplication. So the aggregated rate of n flows is like this one, and this t means the bottleneck throughput. So eventually we get beta equals to t divided t minus delta. That means this one is independent because we already know what is our target link capacity, and delta can be measured from signals. So that means, okay, our first principle, MIMD is essential. This is the first one. Okay, and the next question, okay, if we follow this way, we need to use MIMD. Now, how can we get an end-to-end signal precise enough to take this position to complete this operation? So our second principle is we use the delay and the delay gradient as our precise signals. This is our analytical formulation. I will skip it. Not just show the animation. You can see this is the RTT. We need a base RTT. Okay, and this is the queuing packets. So all these details are in our paper. We can see that this equation holds. This equation holds only when the queue is not empty. And when the flows are window bounded, we can have this final equation that our delay can reflect the window size. This is our observation. So if flows are not window bounded, the window size will be larger than the in-flight packet counts. Okay. Therefore, under specific conditions, our delay can precisely reflect the aggregate window of all the flows through the bottleneck. We have a similar derivation in the paper that which I will skip here, that the degree, it will show that the delay gradient precisely reflects the total sending rate. Okay. So now we can notice the catch. A flow cannot be window bounded and rate bounded simultaneously. So these two signals are precise and mutually exclusive conditions. So our final solution is to use these two control loops together, which we will see later. Okay, I can time. So finally, we come to our OSCA. It's a one-step convergence and readily deployable congestion control. It's a very simple control law, as we can see. And we have 4 challenges to solve. Okay, to actually realize this control law, let me walk through these 4 challenges from the left one. First one, how to measure this delay and delay gradient accurately. Now, the native approach, as we can see from the left figure, we just divide just directly calculate the delay by 2 consecutive samples. But this one, as we can see, in practice, it will lead to great error because our packets leave the link in nanoseconds scale. So if we directly calculate this, we will get big error. So this is what we do. Okay, we use a batch estimation. This is the first one. We just fitting the slope. We get the slope. Use the slope to derive the delay gradient. This is the first idea. The second idea, we slightly change the equation so that we can only calculate the one with constant time and space complexity. So we can easily implement this in NIC. This is the first design. The second design, we use reference state selection. This is a very interesting observation. We found that all previous congestion control, they are actually unsynchronized. They send the data and observe the congestion signals, and they react. But what they are reacting is actually a state. It's not synchronized, as we can see from the left figure. This is the HPCC. Okay, their reference state and their signals are not synchronized. They are not reacting to the actual sender state So for our solution on the right, the OSCA, we synchronize the whole thing. What we are reacting, the signal is reacting to the previous state when the packet is sending. So with this synchronized state selection, we can eliminate many errors. Okay, this is due to the time limit. I will just quick show you. You can see we are not overreaction. Okay, the third design is that we can coordinating 2 loops. Okay, we have a theorem. This is a proof that delay and gradient should be the window and the rate should be adjusted with the same ratio mu. Okay, and that means what we can do, we separately calculate the window and the rate control. We get 2 mu, and then we merge them together, and we apply it back. This is what we are doing in OSCA. The problem is how can we merge them to a single mu? Okay, this is our coordination. The basic idea is we first choose the direction. Okay, we first choose the direction. We use the window part to decide we either accelerate or we decelerate. Okay, and then we decide the magnitude, how much we accelerate and how much we decelerate. So this is the sum of the pseudocode. Okay, all the details we will leave it to the paper. Finally, there are some requests. This is optional. If you really want to, which way I think is questionable. Okay, I don't think mostly we need fairness, and this is optional. But if you really need fairness, we can add a special part, a special AI after the whole calculation, and it will ensure that Oscar can achieve fairness if you want it. This is a padding. So finally, we get to the implementation and overhead evaluation. We implement Oscar and other CC for comparison with DPDK. And you can see that the overhead of CPU. Oscar is just slightly larger than DCQCN, but it's much lower than other competitors. So and this is the testbed evaluation. This result shows the delay gradient calculation. As we can see, with our design, our mean squared error is over 10 times smaller compared with the state of the art. I guess it's timely. So that means our delay gradient is very accurate. And this is the testbed results. As we can see, mostly Oscar can really achieve this convergence in 1 or 2 steps. And this is another evaluation, testbed evaluation with Swift. As we can see, as our design, Oscar can really quickly achieve and converge to its targeted rate compared with Swift. And to give more results, we make a large-scale simulation. As we can see, we mostly compare that with HPCC. Okay, we use it as a SOTA. As we can see, because HPCC target for empty queue, but what we are targeting is the full queue. So for small flows, we have slightly increased the latency. But for large flows, we significantly reduce it. And the average and the tail, we all significantly reduce their flow completion times. And we also their reviewers ask us about the proprietary load balancing, which now is prevalent in AI clusters, and we can show you that our solution also supports proprietary load balancing. So here comes the conclusion. Oscar is the first readily deployable congestion control that can achieve one-step convergence. So our contribution, as we said, we are the first to borrow the big O notation. And we also show you how we can accurately delay gradient can be accurately estimated, and it can be used in our solution to reach the INT level precision. And we also point out that we should synchronize the reference state selection together with the feedback. All this stuff comes from our years of understanding of congestion control, and now we come here. Okay, thank you, and I'm happy to take questions. Okay, thank you.